So you've done some translations and you're thinking, what should I do next? Well, while you reflect on it, why don't we do just that? Reflections. Yeah, been saving that pun for a while. Glad I could use it. Anyways, with reflections, it's a little bit of a new spin on things. Some people would probably say that this is a step harder than translations. I'd say most people. And then we get some really interesting things with inversions, which are kind of another sort of reflection, but it's not quite as tricky going from translations to reflections as it is to go, in my opinion, from reflections to stretches. So this will be sort of a step forward, but not a leap. Our first step on our steps is knowing sort of what we're looking at. And we're talking about with a reflection, it's kind of like mirroring something. And so just like if I had, a line about which I was reflecting something, it would be reflected along that line and be a perfect mirror image, which is kind of like what I have there. Awkwardly enough, I'm terrible at drawing, so it's never going to be very good. And sort of to gauge where we're going to be reflecting or how we're going to be reflecting, we have to consider what we're reflecting about. And usually it's going to be one of our axes. When we reflect about an axis, let's say we've got a graph of, let's say something like this. I don't know, we going like that. And we'll see pretty much this graph in examples. We're going to have reflections going about our x-axis, which will be turning it up and down. So when we reflected about our x-axis, that's going to be a vertical reflection. Vertical. Ugh, cannot write on this thing. And then if we reflect it so that it mirrors about our y-axis, that's going to be horizontal. And we'll see some really clear examples of this in a minute. But before we do, we need to consider that if you have like an axis about which something is reflecting, any of the points on that axis are going to be sort of like the hinge about which we reflect our graph. And so you're going to have points that aren't going to change. And these are called invariant points. And invariant points are points that remain the same on our graph and the reflection of that graph. And I'd argue this is a really quite intuitive word, like invariant, non-variable, not changing. These are points that will stay the same. And so when we are thinking about moving about our horizontal axis, we'll have this sort of point right here that's going to be our hinge. So if we're doing not a horizontal axis, but a horizontal reflection, we're going to use this as sort of the point about which we're mirroring it. And so it'll stay the same. Whereas for our vertical reflection, where we're hinging about that horizontal axis, we're going to have 3 points right on our axis that are going to be invariant points. So enough talking about it without really, wow, nice zooming, Mr. Herman, thank you. Enough talking about it, let's actually go ahead and do it. First thing we'll do is vertical reflections. And I think that we're doing this, I know we're doing this, but I think it's because it's the easiest. And really all we're saying is that if I want to reflect something vertically, I essentially want the exact inverse or additive inverse, the opposite, right, of whatever I've got. So if it's +1, I want -1. If it's +300, I want -300. If it's -2.2, I want +2.2. Just taking the additive inverse of whatever I have as an output, and now my new output should be the opposite. And to do that, it's actually really easy. All I want to do is take whatever my function is and just get the opposite of it by having that negative sign in front. And another way we can do this is instead just putting the negative on the y, which leads us to our coordinate mapping notation of y to -y. So if I want to perform this translation, or rather, sorry, this transformation, I'm going to just replace y with -y, which will lead us to this sort of second form, y equals -f of x. I kind of like putting the negative here because we'll later find out, just like with vertex form, where we had sort of y equals ax minus h squared plus k, this a could be negative. This negative sign is the same one that we applied to that a to flip our parabola. So I like having the negative sign sort of in front of that f of x as opposed to attached to the y. But if we want to use this notation, it would make sense to put it on the y, right? So to produce a reflection, we're just replacing y with negative y, or just applying a negative to our overall function. And we'll see how that looks here in our examples. So for both of these, what we want to do is use a different color or whatever, it's your notes, I don't really care. Produce a reflection by doing y to negative y. And I'll show you two ways of doing this. The first is thinking about it as a function overall and then graphing it. So here's our first function. It's f of x is equal to x squared plus 4x plus 4. In order to do this replacement, we're going to do, well, really we're saying y equals f of x, right? And so y equals x squared plus 4x plus 4. And then if I want to do this replacement with y becoming now negative y, we'll get this, negative y equals x squared plus 4x plus 4. And so to get rid of this negative 1, it's kind of like just as easy as saying, well, let's divide negative 1 off of both sides. This will become positive because we want to graph y in relation to y, not negative y. And then we just have this negative 1 applying to everything. So as you get negative 1 x squared, so just negative x squared, negative 4x, and negative 4. So it ends up being negative x squared minus 4x minus 4. And if we graph it, we're going to form this parabola where it is starting at the same place, and then it's going to go downwards, sort of kind of exactly how you'd expect. And so we got our parabola going like this. This might be the best I've drawn in a long time. I missed. Why would I start gloating? Okay, that's honestly not bad though. Okay, hold your applause. It's fine. So here's what a parabola is going to look like. And what we'll notice is some pretty obvious stuff. First off, it looks pretty obviously to have been flipped about this axis or reflected about the axis. Notice I'm just drawing this the way I'm kind of intuiting it. It's not a rotation. You're not rotating it. You're reflecting it. Different idea. Secondly, our invariant point is going to be where we expect it, right on this axis. So if this is the axis about which we reflect it, any point on that axis is going to stay where it is because it's sort of the fulcrum about which we're doing this reflection. Okay, so that's really handy. Another way I can look at this is if I compare sort of this point here with this point here that I totally missed, consider that the point negative 1, 1, its mirror image is negative 1, negative 1. And so what I'm doing here is I'm just taking whatever values I have. So whatever my x is, I'm going to leave it the same. And then I'm just going to get the negative, the additive inverse of my y. So for any given point, all I need to do is replace y with negative y. So this point here, which is 1, 9, has the reflected point here, 1, negative 9. And that's actually really, really easy for us to use as sort of a tool to perform these reflections. So for our next one, we're just going to reflect it without even worrying about the function first off. I'm going to start by, let's use purple because purple's perfect. I'm going to start by looking for my points that are invariant points, and that's anything that is on our x-axis. So 1, 2, 3, those points are on our x-axis. And then let's go ahead and let's find what points we have. There's one here, right? So I'll kind of put a little circle on it. And so this point is an important one, negative 3, 4, because it's something I can actually see. And so if I've got that point, actually, you know what? I got a way better idea. Let's label that in red. Oh, I'm so smart. So this point, negative 3, 4. Another good point here at negative 1, negative 6. This point here is really nice, 0, negative 8. And then there is no other points in here, but that's more than enough to work with because what I'm going to do is I'm just going to take this and do y replacing it with negative y. So instead of positive 4, I'll get negative 4. So I'm going to go to negative 3, negative 4, and draw my point here. Okay. Next point is negative 1, negative 6. So I'm going to go to negative 1, positive 6, and draw that. 0, -8 becomes 0, +8. And then I've got this really nice guideline that I can use. So I know that this doesn't quite reach to -5 on our x. So I'm going to start before -5. I'm going to come down. I know I go through this point, -4, 0. I do a nice little tap there on -3, -4, back through -2, 0, up to -1, 6. I do have a maximum above 8, so I'm going to do that. And then I'm going to totally miss the dot there. And this one really starts going down. So end up with this. And the nice thing about this is if I'm going to do my sketch, I can kind of clearly see where my original function is. And I can really clearly visualize, yeah, there we go. I just flipped it about that axis. So it's exactly like the work we were doing with our absolute value graphs, where we're just taking that and flipping the parts so that they're positive where we want them to be positive. But in this case, it's the whole thing. Now, if I wanted to do the function for this, what I can do is just say, well, our translation of y to -y gives us, well, just the negative of this. So our new function, let's call it g of x, just because I feel like it, is going to be the negative. So -x cubed, plus -5. Why not we just write -5x squared minus 2x plus 8. And that all works out really nicely for us. If I plotted this into my graphing calculator, I would get whatever the purple graph I drew here is. I'm going to put an arrow here. So that's nice and easy. And it's probably not too much of a surprise that if we replaced y with -y to do a vertical reflection, what do we do to make a horizontal reflection? Well, just the exact same thing, but with x, just to replace it with a -x. And so that is what we find is exactly the case. Now, with these, I probably could have mentioned this before. It's sort of intuitive. If you are flipping a graph, you have to worry about flipping its domain and range as well. Domain is not going to be as big a deal unless you're dealing with like a radical or something. But in that case, it's actually not going to be too hard to figure out. Range is a little more intricate because you're going to be dealing with more functions, for example, like x squared or anything that has a degree of an even degree. But in the end, really, you just got to sort of see what graph you come up with, and you can go from there. If you're just given the domain and the range, then just think about, if we're flipping it one way, we're doing the opposite. So if you know your domain for something, a radical, let's say, is our set x is going to be that x has to be greater than 0. Let's just say it's root x. Then if I do the opposite, well, that means our sign here is just going to be the opposite. So for this new one, if I perform this translation, or rather transformation, it's going to be x, so the set of x such that x is now greater than or less or equal to 0. Oops, I said these backwards for one of them, but whatever. So let's look what that looks like. And let's do the reverse order here. Let's take x squared plus 4x plus 4. And instead of worrying about it for the function, let's just do our flip. And so I'm going to start by looking at my points on my y-axis because that's our invariant point. So boom, this point 0, 4 is going to be an invariant point. And then any of these points that I see, so like this one, 1, 9, I'm going to take it and just get the additive inverse of my x coordinate, which I know is -1, and it's going to stay at 9. At this point, -1, 1 becomes 1, 1. -2, 0 becomes 2, 0. -3, 1 becomes 3, 1. -4, 4 becomes 4, 4. And so on and so forth. You guys sort of get the picture, I'm hoping. So that's not too bad. Oh, and I nailed that. Honestly, okay. Perfect parabola. You're literally never going to see anything better. Get me to the Louvre. I'm worth it. If I actually apply my -x into this function, here's what I'm going to get. I'm going to sort of have like we did with the horizontal translations, where it's more or less we're doing a composition. If I've got f of x equals x squared plus 4x plus 4, and I perform the operation where I'm replacing x with negative x, our new function, well, let's call it g of x, is equal to negative x in brackets squared plus 4 negative x plus 4. So we can't just apply a negative to everything and then cross our or snap our fingers and be done. We actually have to put that negative x in as if it were like a composition. And so what we're ending up with, y or g of x, whatever is not really relevant, is x squared. This is going to be negative 4x plus 4. And this makes sense because, look, x squared, that means a parabola opens upwards. Our leading term has a positive coefficient. And plus 4, our y-intercept is exactly what we expect it to be too. Gorgeous. Let's actually use the graph method again. Oh, there are network connectivity problems. That's awkward. I'm going to pause this video while I fix that. Okay, I got it all fixed up. Let's do this horizontal reflection here again. Okay, I'm going to start by looking for my invariant point. That's this right here. And then I sort of know what I'm doing now. So instead of actually writing all the points down, I'm just going to sort of find a point that I know it's on a line. This one's -1, -6. Okay, great. It's 1, -6, right? I'm just kind of walking across my axis here in just as many steps as I need. Okay, this is at 1. Okay, so it should be at 1. Great. This one's at -4, so it should be +4. What are some other good spots we could do? None there, but how about this one? We're at -3, so let's go over to, sorry, +3. Almost missed. How awkward. And then notably, we kind of got this point somewhere in there. Great. Nice. Okay, that should be enough to work with. I'm going to go ahead and draw my function now. We're going to go through here. We're going to just have a nice little peak there. I missed that point, awkward, but I'll draw through it because I know it's there. And yeah, close enough. Perfect. Beautiful. And voila, we see that my graph, although this looks like a 2-year-old did it, my graph there does match or does look like a pretty nice little reflection there. If I were to take this function and actually do the replacement x to -x, what I'm going to get is this. Our function g of x is going to equal to -x cubed plus 5 -x squared plus 2 -x minus 8. And what happens is, well, cubic, that's going to give us -x cubed plus, well, if I square a negative, it disappears. So plus 5x squared plus -2x, well, that's minus 2x, and the 8 stays the same. And so really, really notably, only our odd terms are actually going to flip sign. And by odd terms, I mean terms that have a degree that's odd. And this is kind of a big deal because that also means anything with an even power. So 0, right? This is kind of like saying x naught, x to the power of 0. This didn't flip. It stayed as -8. This squared, well, it was started as 5x squared and it ended as 5x squared. It ended up staying the same. That's interesting. So when we did our vertical reflection, everything changed. But here only some of the things are changed. And that it's kind of a big deal for this next question here that I'm going to ask you. And that's this. What functions, if any, will produce the same graph for both of these transformations? So for the vertical reflection and the horizontal reflection, producing the same graph. And you think about that for a second while I prove that there are definitely some. If I take the line y equals x, so let's draw that. Our line here, y equals x. Never mind that. So there you go. It's got both arrows now. If I do a vertical reflection, well, this is going to be up here, right? Kind of like that. Good, 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 good. So that's our vertical reflection. You can kind of see that. Now let's say I want to do a horizontal reflection. Well, this tip kind of goes over here, right? And then this tip goes over there, reflecting. And you'll notice I drew the exact same graph. So y equals x is an example of this that works. Y equals x works. And so think about this. What other kinds of functions would match? Another way to kind of spin this is if the function's graph is based, of course, on the function, what sort of functions will end up the same way when you mess with them by replacing everything with a negative versus only the x with a negative? And it goes back to what we were talking about with our previous one. So if we had x cubed plus 5x squared plus 2x minus 8, that was our previous equation. We noticed that when I did that first time where I just did y to negative y, everything switched signs. But when I did x to negative x, only 2 of our 4 terms changed signs. And that's based on the fact that when I square or put to the power of 4, or anytime I multiply an even number of negatives together, I get rid of that negative because a negative times a negative is a positive. It's kind of a dead ringer then. In order to make this work, what we need is a function that only has odd powered terms. And this is referred to as an odd function. An odd function is one that needs to have only odd powered terms. So the degree here is 3 of that term and 1 of this term. They're both odd, right? That, if that's all we have, so if we had just x cubed plus 2x, this would be an odd term or an odd function overall. This, another way of thinking about this is if I kind of calculated the area under our curve at any given points, right? So if I said like at -1 and +1, the area under these curves would be exactly the same, but opposite, right? And so if I wanted to compare, the amount under my curves at -x through to x, it would always be 0 because they're exactly canceling each other out. That would kind of lead you to the assumption that, well, is there such a thing as like even terms? And yeah, an example of that is x squared, which I'm accidentally drawing in a color I already used. But x squared only has even degree terms. It's only got 1 and it's squared, that's even. And instead of it producing exact opposites, both sides are exactly mirrored. It's all the same. And obviously this will not satisfy a condition, but it is a cool little other thing. Okay, let's talk about our next idea here. And unfortunately, this is sort of an older version of the note, so I'm going to add some things as we go along. But it's kind of a big deal what we're doing here. And that's called an inverse operations. And so inverses is where we take our function and we're going to replace the numbers, or rather the variables x and the variables y. I'm going to start by erasing this. This is not what that function is. It's honestly not even close. So we can get rid of that all the way. What I'm going to do instead is the function f of x. Oops, let's do it in vertex mode. So our coordinates for our vertex, a value happens to be 1, so that's easy. So it's just going to be x. We're at +2, so it's -2 squared minus 8. So here's our function. And another way I can write that is like this: y equals x minus 2 squared minus 8. So what I'm going to do is I'm going to do a inversion by wherever I see x, I'm going to put y. And wherever I see y, I'm going to put x. And so I get this: x equals y minus 2 squared minus 8. Interesting. Now, another way we can look at that actually might be a little more intuitive is this. If I have my coordinates, just like I replaced x's with negative x's and y's with negative y's when we were doing reflections, now when I have a point here, and let's use red because that's the color we're looking at, this point is 5, 1. If I want to replace y with x, what I'm going to do is do exactly that with my point. So I'm going to have 1, 5 instead. So 1,5, well, that's here, here. Spicy. Let's find some other points. Well, here's negative 4, 4. So I'm going to have 4, negative 4. Okay, well, that's totally did that backwards. So we have 4, negative 4. So we're going to have negative 4, 4. That should be up here. There we go. Brain, good job working. All right. What else have we got here? Our next sort of point. Let's go down here. Perfect. We've got 3, negative 7. So it should be negative 7, 3. Cool. 2, negative 8. So it'll be negative 8, 2. Here we've got 1, negative 7, so negative 7, 1. And one thing you should notice right away is while I'm drawing this, this is no longer a function what we're doing, right? We have something that's not passing a vertical line test because we've got 2 dots here. But let's carry on and let's see what we end up with. Negative or 0, negative 4 is then going to be negative 4, 0. Swapping those. What do we got? Negative 1, 1. So 1, negative 1. And let's do one more point here. We've got negative 2, 8. So it's going to be 8, negative 2. And I sort of see the pattern here. It's the same parabola. It's just swapped onto its side. And totally missed there. I promise I'm better at drawing these on like actual paper. But we get the same sort of parabola or parabolic shape. It's now just rotated sort of on its side. And I have to kind of wonder, what is the rotation that we're doing? Well, horizontal translation, we rotated about the y. Vertical translation, we rotated about the x. So we base that sort of understanding on what points didn't change. So what points would have the same value on this translation? Well, if we switched the x and the y, our invariant points, the points that don't change, would be ones that have the same value for x and y. And that means y must equal x for our line of invariancy, or the line upon which we're actually going to be reflecting. So let's say negative 8, negative 8. That would be here. This is good enough. Push that through the origin. Perfect. So, and look at that. Other than the fact that I can't draw, we're crossing those same points all the time. This one is particularly bad, I recognize. So let me edit this because it just looks terrible. This graph should go more like this, up to there. And so now we're actually closer to that invariant point. This one I actually managed to nail. Good for me. That is our reflection. We're actually reflecting about the line y equals x. Cool. Now you'll notice we had another kind of point here that sort of remained quote unquote the same. That's totally coincidental. Let's see sort of what we'd get from this. Now, if I wanted to graph this on a graphing calculator, I need to graph it with our y value as sort of the term we're solving for. So I need to solve for y here. I'll start by trying to isolate it by getting rid of this 8. So we're going to get x plus 8 equals y minus 2 squared. Then I'll perform the opposite operation here, which is square rooting. So I'll end up with root x plus 8 equals y minus 2. And finally, I'll add the 2 over. So I'll get 2 equals y. One thing to keep in mind, if I just consider the positive side of this, well, this kind of explains why I have 2 parts here, right? If I cut this in half, I've got 2 functions, but together it's not really a function. And that's because I'm sort of considering the positive and negative of x plus 8 all at once. Nifty. And that leads us to a really tricky sort of problem here, that when we do an inversion, a lot of times we're going to get a function that does not have an inverse that's a function. So this parabola here, if I do its inverse, I'm not going to get a function. And we can see that pretty clearly. So I'm going to get rid of this line here. I'm going to try. My eraser size is about gigantic. Let's get rid of you. Great. And so what we see is that we don't have a function. So if I did my like vertical line test, obviously this isn't working, right? This is not a proper function. Even though it makes sense how we got it, it's not a function. It's not working for us. And you can actually see where this is going to be if we just focus on our original function and do a slightly different test. So I'm going to erase this. If you needed that, go back like 5 seconds or pause your video, deal with it. Instead of doing the vertical line test on this function, we're going to do a horizontal line test. And if my horizontal line test passes through more than one point, that means my function will sort of fail that test. And it means that the inverse of that function will not be a function itself. So what do I do about it? Well, I can kind of strong arm it like I did with drawing and sort of consider, oh yeah, if I consider the positive and the negative, yeah, I can smudge the numbers. Or I can do something called restricting the domain. So I know our problem kind of comes from here, right? This is the point, this point, our vertex is where it starts failing that horizontal line test. Everything above that kind of spreads out on both sides. So if I can restrict the domain so that I'm only actually going to be looking at this side or this side, then I know that I'm going to have something that the inverse of which will actually be a function. So the inverse of x minus 2 squared minus 8 is not a function. But the inverse of x squared minus, or x minus 2 squared minus 8 such that x is greater than or equal to 2 is a function, right? And let's write that. So our x minus 2 squared minus 8 such that x is greater than or equal to 2, this group here actually is a function on its own, that set. But the overall function itself is not. Interesting. So here's another one, and let's see, let's do that horizontal line test and see if anything's going to be bad. It kind of almost looks like it right here, but this is just still barely slanting. So I'll get rid of the suspense on this one here. This part actually does work for a horizontal line test, so don't worry about that. If we drew it anywhere else, no, that's obviously fine. That's obviously fine. Great. So this will in fact pass our horizontal line test all the time. So to do our inversion, what I'm going to do is I'm going to first consider the formula. So if I've got y equals x cubed minus 4, or maybe I'll write that, whatever, as y equals x cubed minus 4. To do the inversion, I'm going to have instead x equals y cubed minus 4. And all right, if we solve for y, I'm going to add 4 to both sides and then cube what's left. So I'll end up with this, y equals the cube root of x plus 4. And the nice thing about cube roots is that you don't have to worry about the positive and negative side of it. It can handle either. So we don't have to do that plus minus. And that's kind of a good indication that what we have is a function that actually will produce an inverse that's also a function, which is nice. Okay, so if I graph this out, I would get a function that looks like what I'm about to graph just by hand. But I feel like practicing our sort of techniques here. So let's go ahead and let's do that. All right, with this, I'm going to go ahead and draw out our function and see what we've got. Let's start with this point here. We're at 0, -4. So that means we're going to have a point at -4, 0. Okay, our next point here is at -1, 5. So it's going to be 5, -1. And I realize I must have done that backwards. Oh yeah, it's -5, -1. Sorry, that's my mistake. Okay, this is going down. Kind of looks like we're going to run into something here, but that's going to be tough to judge. Actually, I know that's going to be at -11. So -2, -11 means like -11, 2. So we're going to have a point sort of way out here. What else do we got? We got 1, -3, so it's going to be -3, 1. We've got 2, 3, so we know it's going to be at 3, 2. Awesome. What do we got for this next one? Our next one, well, 3, we don't have anything matching, so that's as good as it's going to get. 3 is way past. So we actually create this sort of function looking like this. Now I will recognize, I'll be the first to tell you I didn't draw this very well. So in fact, I'm going to just try again. All right, it's a lot more dramatic here. Yeah, that's worse, I think. Okay, well, last try. I'm just going to do my best. Hopefully people aren't too disappointed in me. Yeah, that's good enough. Yeah, good enough. Okay. Whew. We can breathe again. Notice that our point here, our invariant point, is right at that line, y equals x. So that's awesome. If I drew that line, it would cross right through it. And that would match the graph here. Cool. I think that, again, and this is something we found with our test, if you can go through this and you can do the work on just the graph, you're going to have a really, really, really good time. One other really cool thing is that with an inversion, you can actually tell a function is going to be an inversion when it's composite of f and g, or rather you can tell this function and this function are inverses of each other, because if you have f of g of x and you have g of f of x, they're going to equal the same thing. So inverses will equal the same thing, and that's always going to equal x. And I guess I'll prove that to you now because I've gone ahead and done it. So let's call red f of x and purple g of x. Let's go ahead and do that. So let's start with f of g of x. So I'm going to have root, or cube root, sorry, x plus 4. And that is going to be cubed minus 4, because we're just replacing this x with g of x. These two cancel out, right? So we have x plus 4 minus 4. Positive 4 and negative 4, that's going to equal just x. Cool. So that's a good sort of a dead ringer that it'll work, but we have to prove both ways work. So here we go. We've got x cubed, and then we're going to have x's are going to be replaced with f of x. So that's x cubed minus 4 plus 4. And so with this, we've got an x cubed minus a 4 plus a 4. So we just have the cube root of x cubed. And that, of course, does equal x. And so both these equaling x, we know that's an inverse for that reason, too. Pretty cool. Okay, so we're reflecting about the y equals x line for that. So here's just sort of a run over of everything we're reflecting on reflections. Ha ha hoo hoo ha ha. Vertical, we're replacing y with negative y, and we're reflecting about our x-axis. Horizontal, we're replacing x with negative x, and voila, you're going about your vertical axis, which is your y-axis. And then finally, inverse is where we replace y with x or x with y. But I mean, either way you write it, you're doing both, and it reflects about the line y equals x. The last thing we're going to have in this video is the fact that you can mix and match them. And it ends up being kind of interesting, I think, but we'll see that it's already really not too bad. And we can do all of these without even worrying about the function. So here's how I would do this. If I want to replace y equals f of x with negative y equals f of negative x, that just means I'm really doing this. I'm going y becomes negative y, x becomes negative x. Okay, and so if I take a point here, this is negative 1, 4. I'm just going to take this and do the additive inverse, so it becomes 1, and this additive inverse becomes negative 4. Okay, cool. So that point goes there. Next point, this is 0, 3, so it's going to stay as 0, but it's going to become negative 3. This point here, 1, 0, is going to stay at 0 for the y, but become negative 1. Negative 3 becomes positive 3. Sort of, and at this point, you can kind of see my pattern here. We're creating the same parabola. but now going like that. Cool. And so I can follow that same kind of technique for all of this. In this case, we're replacing x with y and y with negative y. Okay, very interesting. So with this one, what I want to do then is I'm probably going to want to do this y with negative y first. So I'll go ahead and do that. Here we go. This point again is -1, 4. So it's going to convert into -1, -4. And then I will do my flip so it becomes -4, -1. So the point -4, -1 is over here. Okay, let's take another point here. So we've got 0, 3. That's going to convert then into 0, -3, which converts then into -3, 0. -3, 0 is right here. Okay, interesting. What else are we going to have here? Oh yeah, sorry. I know why this is looking terrible because I'm using the same color for both these things. Let's look at some more points. This is 1, 0, so that's going to become, well, 1, 0 again, so it'll end up being 0, 1. Okay, this point here, -3, 0 becomes -3, 0, so 0, -3. And at this point, you should probably see sort of our parabola forming here. Cool. Oh no. Now keep in mind, we're really starting to mess with some things here. So our points here that are quote unquote invariant, because we're doing 2 translations, not everything's going to stick. So don't worry about our invariant points as much on this. I'm going to leave the last one as an exercise for you if you want. If you want me to double check it, I'm happy to go ahead and do that for you later on. But for right now, should be just about good. These ones here, you should be able to kind of find out what transformations we're doing by going backwards. So I'm going to leave that for you guys as well. Hopefully this video was helpful. I will see you in the next one.